Cool. We're back. Small group today. That's all right. Figure we'll hold the brunt of the work for everybody. It should. All right. What do we want to start with today? I know we're working through Module 4 project. Anything coming up? I mean, finite elements, that kind of work.
Just getting started on 5.
Oh, getting Module 5? Okay.
So
yeah.
How does we do without module 5 and the project 5 to do without now on time and then we did that?
Module 5, so we can pull up, here I'll pull up our schedule. So goal is for today, like wrap up any questions on project 4 so that tomorrow we can be done. And then Friday I'll be here, but if you're taking off for Thanksgiving, like don't worry about it, because project 4 will hopefully you'll be done with that without any questions. And then when we get back from Thanksgiving break, that whole week is either review, so if there's any questions about anything, like even like module 1, like how do I do this FizzBuzz kind of problem, we can go back and look at that. It's all connected, like and if you take the skills that we've been working on, like linear algebra and all this, and go back and retry some of the module 1 stuff, you'll probably find that you can do it a lot faster, and a lot of it makes a lot more sense because you have so much experience now. So it's all connected. It's all just practicing, getting comfortable, getting computers to do things for you. But that's that last week, is that we'll have those 3 days to work on either module 5 or any other questions that come up. Usually we have like those 2 weeks after Thanksgiving, but this year just the 1, so it feels like I just call it a day. Let's just go home. But I don't know. We'll get there.
Good question.
Yeah.
Can you, starting on module 5, talking about Taylor expansion?
Yeah.
And truncation error?
Yeah.
Can you explain kind of how truncation error, how it's calculated, and then how it changes when you're solving for higher order derivatives? Because from taking a first order derivative, truncation error is just, time step to the first, whatever that might be.
Yep.
And then does it scale up exponentially as you go to like second order derivative? If you take the second derivative, now truncation error, h squared versus just h.
Yeah, so do you mean like if we have some function that's some function of, I mean, time and space are kind of interchangeable, whether we want to say that it's yeah, whether it's a function of time or a function of space, it's still just a function, one kind of independent variable. So you can always do like a Taylor series at any point. So I can say that it's f of yeah, let's call it like x0 plus f prime of x0 times x minus x0 over 1 plus f double prime of x0 times x minus x0 squared over 2 factorial, and it continues that way. And it's exact as long as you have an infinite series of polynomials. But what we, at least for like Euler integration, when we were looking at that, and then same thing for module 5, we're looking at boundary value problems where we're turning these derivatives into finite difference problems. So I can rearrange this equation and say, what is the derivative at some point x0? So f of x minus and there, like, it's not anything new because it's really just saying like delta f over delta x equals the first derivative. But I ignored
Chopped off the extra term.
yeah. So I ignored all this other stuff plus everything that is like order x minus x0 squared. So the bigger.
Wouldn't that be divided by x minus x0?
Yeah, I mean, we could divide it by.
Because to get f prime of x0 by itself, you had to divide by x
Oh,
minus
yeah,
x0.
yeah, you're right. Okay. Thanks. So, and that big O notation is just kind of like, what is the big term? So the 1 over 2 factorial and that f double prime, those are usually not, they're usually just like some number, just a fixed number at that point.
So I'm saying if you're taking truncation, you're only looking at the largest term that you're chopping off first as the quantity of error, basically. Because all the future terms, to the third, to the fourth, to the fifth, are just going to get smaller and smaller.
Those are going to be, those will keep getting smaller because usually we're not doing a Taylor series and looking at like x. So if x0 is 0, we're not trying to evaluate it at 10. We're trying to evaluate it like 0.01 or
You're assuming the steps are less than 1.
Yep.
Because if they're greater than 1, then the higher order is going to lead to greater error.
Yeah.
Right?
Yeah.
But if they're less than 1.
So we want small, relatively small steps, relative in the sense of compared to x.
So then if you were to solve for the second derivative, basically you'd have a higher error term.
Not necessarily, because for the
would always be the same order of error.
It depends on if we're using a forward difference or a backward. Like if we're using forward, backward, or central. So forward and backward difference methods all have the same order, delta t, delta h squared, like whatever our step size squared. But if we're looking at central difference, now we're taking a forward and a backward and adding them together. So we end up with a like delta t squared error.
So this order of error here is just delta t, basically it's to the first.
Okay.
And that's just saying how far off you, basically what your range, how far off you'd be from the exact solution.
Yeah, because I could take. I could also say, well, oh yeah, I guess I should have done this, right? So this one becomes negative. That one's positive. This is f prime. Yeah. So now I could take the second one and the first one and add them together, or any kind of combination. But if I add them together, then let's subtract them. So that f of x0 is now 0.
So that becomes the central difference method.
Yeah.
You subtract them.
Yep.
Because you're taking essentially 2 time steps, right?
Yeah.
Centered around
0. That. Yeah.
And so central difference should be a higher order of accuracy.
Yeah.
Because you're now taking more information in.
Mm-hmm.
And therefore your error should be smaller. It should be what? Delta should be h squared, essentially. Because you have a smaller order of error.
Yeah. So all the even terms end up canceling out, and I end up with.
Gotcha. So when you solve for the derivative, you're going to take h cubed divided by h to get your order of error.
Yeah. And then this one's 2h like that. So we end up with order h squared because we did forward and backward.
Yep.
And basically took the average
So
of
the more
those
time
two.
steps you're taking, the higher accuracy and the lower order of error you're going to, the lower error you're going to get.
Yeah, because you can think of it as like how many terms in a polynomial are you assuming this function has?
Yeah.
So Euler, if we're just saying it's 2 points, then it's a straight line. If we're saying that there are 3 points, then now it's a parabola. So we'll get delta x squared kind of.
Okay.
Yeah.
So
Yeah.
for part E on a project, I can't get into like the extra FE material to get like the plot.
Oh, really?
Yeah, it's giving me like a 404 not found.
Oh, it's probably missing that .md
I think
again.
it only works on like the top.
Yeah, the top link works. Go to the top of the project. And the
The
link
bottom
works.
2 is a problem.
That's a weird thing.
Yeah.
Sorry, which link is broken?
So
it's in part D.
The top one.
They're all broken.
Well, just
Okay.
to the
I'm trying to get to
You go up.
part 3.
It's when it talks about using the clever font.
Okay. In this note, look at.
Extra FEA material. So all those ones, except for the top one, are broken.
Yeah, you're right. They don't have the .md. You can always fix it with like adding a .md at the end, and then it'll pop you into the right notebook. But yeah, I need to go back. I thought I had gotten all of them, but there's a difference when you're building the website. You can leave that .md off, and it works. It's like, yeah, no problem. I know exactly what you're talking about. But when you're building Jupyter notebooks, it's much more specific. It's like, are you looking for .md or .ipynb, .dat? Bless you. Yeah, and inside this extra FEA material, there's it has introductory stuff about like how these elements work. They're 2-node single element kind of beams. They only have stretching and compression like force, so they can't maintain any moment on them. But that's okay. That's all we're dealing with in this case anyway. And the last thing, like if you set up your variables the same way as this kind of notebook, then actually let me run through everything. Kernel restart run all. And you can use this like post-processing function to like either create a graphic or just, rather than interact, you could just run f of 5 to get, like if you define the same function with the same ix and ru and all that. Yeah, usually, let me give, because usually there's questions about like, how do I get that, how do I make this plot? So let's give it a shot. Yeah, okay. Usually there's a question about it, but like, I don't want to tell you what you need to know, what I think you need to know. But let's do this. X. Delete all that. We got to start from the beginning, load everything in. What did I call it? P, capital PLU? I called it nothing. Okay, so what I'm doing here is I'm setting up my problem. I'm using LU to decompose like lower, upper triangular matrix. The pivot matrix I already know is a diagonal matrix, but even if it's not, I can include it in the solution. I can say like P transpose times that right hand side, and that'll pivot the equations, and just renumbering them so that I don't run into problems with Gauss elimination. And then I end up with all these displacements. These are all my all the nodes that can move, this is where they ended up. And so here, this is like node 2x, node 2y, node 3x, node 3y, node 4x, node 4y. So node 4y is the biggest downward displacement. So as we're trying to figure out how do I get the total structure to be less than 0.2, it's this node. That's the one thing that we care about. It's like node 4 in the y direction, and then the rest of them. And a lot of symmetry because we have like load right down there, so a lot of the y displacements are the same. X keep increasing as you move further along. Cool, so I've got that. In total, the displacements, like if I want to describe what were all of the displacements of nodes 1 through 7, there were 14 displacements, but I only solved for 11 of them. So I need to say all of the displacements are 0, or I mean, you can set it up however you want, but one way to do it is create a displacements that are all 0, and then I'm going to say 2 through 13 are U free. So now I've got node 1x, node 1y, all the way through node 7x and y. Kind of setting up that total, what are, from this structure, where did everything go? And do I want to call this, I already called it F. I want to use a different, here, I'm going to call this like FEXT. It won't change what I'm solving, but just saying these are external forces applied. So that all of the forces, when I look at what is the force on every node, is going to be E times A times K, where K is that full 14 by 14 matrix at U. Now we start, it fills up, like we didn't apply forces, like our original, let's look at this. FEXT. Originally our force vector looked like this. This was all of the applied forces. And now I'm solving for all the applied forces plus reaction forces. Everything that's like 10 to the negative 14, 10 to the negative 13, those are just floating point errors that all stacked up. Like they're all 0, but it's not quite 0 because we're doing computer math on it. So we're adding a little bit of error because we're using a computer. So 0 150, and then 0, 0, 0, 0, 0, negative 300, be applied, 0, 0, 0, 0, 0, and then another 150. So we have 150, 150, and 300 in the middle. So it kind of makes sense, at least from what I would do with hand calculation. That's all my troubleshooting steps. I don't like to jump into like trying to plot something until it actually makes a little bit of sense. Or maybe like jump in and plot it and like, why doesn't that make any sense? Okay, now let's take a look at what that structure looks like. I can try just grabbing this whole function. Let's just try to run it. F of 5. And it's going to tell me R is not defined. It's like, well, what was R? So we'll come back up, figure out where was R defined. So R was defining all the locations of the original nodes. And it uses IX and IY to actually draw triangles in every spot. Otherwise, you don't see, like if all you do is plot the node locations, then you don't see everything. So I'll copy this R. Let's put a new cell right above it and say that R is that. And then tell me nodes is not defined. Like, well, what the heck is nodes? So the nodes is this one. So I could grab these two lines. Or I guess these 3 lines, because I want L of 300. Hey, get back here. So now I have R defined for each of the in there. And now that I have R and nodes defined, it'll use that function and show me like what the original structure looks like, and then what the structure looks like when you apply the force. So with all those like nodal displacements added in. You can also get this nodes is when we load in this K array, we could also say nodes equals and that gets popped. It's saved inside that FEA arrays NPZ file too. So if you're using like finite element analysis, this is usually how FEA works. I mean, it's always how FEA works. Is you have your elements are all defined by nodes. So you define a whole bunch of locations in space. Here I've got 7 different XY locations. And and then the element array tells you how each of those nodes is connected to each other. So some of them, like element 1 and element 2, both share node number 2. And then node 4 is also connected to node number 2. So it's saying like, here's all the points in space that I care about. And then the elements actually should say like, how are they connected to each other, the element array. No, you don't need all that information to like just do the solution, like for the solve k comma f, but it's kind of cool. See behind the curtain of that FEA solve button. But the main things that you would need, you have to get that R defined. U is going to be your actual like total displacement, so displacements of every node. And then F are what are the forces on every node.
So basically, trying to understand when you're taking numerical derivatives and get the first derivative, you take your xi plus 1 minus xi divided by your times that. Makes sense. When you get into the second order derivative, that's where I'm losing it a little bit because here it's talking about instead of doing xi plus 1, you now have to do 2 time steps. Xi plus 2.
Yeah.
Why can't you take the second order derivative? Just use 1 time step.
You're trying to get it to the point where you can get rid of that prime.
So by taking the second time step, or 2 time steps instead of 1, you can eliminate that. Okay.
Yeah, so you want to take that function plus that, like somehow this plus that, but this one plus the case. So that the only like derivative term for low order is that double value.
Okay. And that's what then this is down here. It's after all that substitution, basically. Okay. Yeah. So you're saying basically.
Yeah.
So what I took this equation here, and I said, all right, I know what that prime of xi is because that's what was previously calculated right here.
Yep. Yeah, you can.
I can just substitute that in.
Plug it in there.
When I substitute it in, I don't get this. I guess I'm very close to it. Where you take f of xi plus 2, usually what starts there, minus 2 f of xi plus 1. But in this, I just have plus f of xi, and it says minus 3.
Oh,
F of xi.
I think it is just plus.
Okay, so if it is just plus 1, that makes sense because in the formula down here, it's just plus 1.
Yeah, that's gotta be a typo then, because I don't think there is a -3.
But then my next question is, in the denominator, it's just h squared. It's your time step squared. I would have had 2 times the time step squared because at some point you have this 4h squared divided by 2 factorial.
Yeah.
Which gives you 2h squared. divided out, you just have this whole numerator divided by 2 times h squared. But that's not in here, and these are, fairly close.
So you have to divide by 2.
Yeah, divided by 2. Because at least from the map, I can see it seems like a 2 is missing somewhere.
Yeah.
That's true. It's pretty close. Doesn't really change all that much. Yeah, great. Okay. And then what's the maximum error between numerical and actual? That's basically not just taking at each of these points, taking the difference here.
Yeah.
And finding the max, and this is obviously well, that's what I see change. This is just flying.
Yeah.
So
Oh, I see.
it's just, that's why
Yeah,
it didn't change.
fine.
It plotted. So I'm doing the second derivative. Truncate started. So that's much closer, without the 2.
Yeah.
So I don't know where I went wrong. Other than the fact that here it says you truncate values by 2, when you take your second order derivative. Then it was removing 2.
Oh, like, so here we miss.
Or you're saying you're truncate. Okay, gotcha.
Yeah.
You're just removing.
Yeah.
Because you're looking at 2 time steps instead of 1. Now you need to limit your data points, basically.
Yeah, your last derivative depends on the next 2.
Yes, you need at least have 2 points forward. Yeah. So if I did that wrong somewhere, to miss a 2, should the 2 not be in there?
Be a negative 2.
So basically, we have f of x out, which is 1 minus 2.
Okay. Yeah.
So then the negative on the side you flip over here, positive 1. Because you have negative.
Okay. Negative 1.
Because you have 4h squared divided by 2 factorial. There's something I'm missing when I plug in. When I plug this back in, should I be having an error term somewhere in there? Should there be some of this? Should there be some of this truncation error?
Yeah,
that gets plugged in here. But does that affect the fact that there's a 2 in the already now in there? You can't click get math. But again, just a little closer than if I were to divide by 2.
Yeah, the two is even bigger.
I'll try it out.
Okay. Yeah. We're just curious.
Yeah, that's right.
Okay. What you can do is you have something like input, plug in that area into the solution and see what the even if you're just like the area should be something application like the dogs like yeah, more yeah, give that area of the you convert the K into yes.
What? How'd your poster session go? Actually, not bad. Yeah. What do you do? Just talk for like, what? Was it kind of similar to the like actual presentation where you're just presenting to somebody all the time?
Yeah, except it could last for like 5 minutes. Like anything close to
Not close to like that.
yeah, even for like when they come to your thing, maybe like max 10.
Yeah.
Yeah, max 10 minutes.
So you guys had a plan
like
what
we
you were
were
gonna say, or was it just kind of like all
during our day at least, they only had 2 judges.
Yeah.
So I mean we just beat on Jason. So we were the second to last group to go. They just wanted to get out of there. We were already like 20 minutes overtime by the time they got to the table. So he's like, I already know everything about your project from last semester. What have you done since then? Only tell me that. We presented like statement things like good job. And that was it.
That's it. Like, all the videos gonna try and share with our group just kind of
He will.
oh boy.
Oh boy. Yeah, I can't wait.
There you go.
Very the and then oh, because it's going off the absolute value of that reaction. That's that reaction is going off so I could just drag. Down the absolute value. Oh, so it has to be over two. I mean, here, all of the structure is held up tension. So we don't need any EI. And you can definitely do it through but it's more like this structure always has a certain kind of line increase. Those all of this, like every one of those things is an increase. Same thing with your line increase variable I and all this place increase. Yeah. So you can use that. When you post the variable one is 2.2.
Hello.